Hello and welcome to lecture 24 of our Essentials of Semiconductor Device Physics course. In this lecture we're going to discuss doping. So last time we used the expressions for the concentration of free electrons and concentration of holes to find the Fermi level in an intrinsic or pure semiconductor. We saw that because the concentration of free electrons must be equal to the concentration of holes, it follows that the Fermi level is in the middle of the band gap, like it's represented here. Now in this lecture, we're gonna discuss a process called doping, which is used to control the concentrations of electrons and holes. So if we change these concentrations, they will no longer be the same, and the Fermi level will change as well. And this is what we're going to learn in this lecture. Okay, so let's begin by defining what is doping. When we dope a semiconductor, we insert what we call an impurity atom into the semiconductor, and it's these impurity atoms that will contribute to changing the concentrations of free electrons and holes. So we control these concentrations through the concentration of impurity atoms. That's something the engineer chooses to get the electrical properties that the engineer wants. And when we dope a semiconductor, we can also call it an extrinsic semiconductor as opposed to intrinsic semiconductor. And there are two types of doping. When we n-dope a semiconductor, we increase the concentration of free electrons and reduce the concentration of holes. And when you do p-doping, we decrease the concentration of free electrons and we increase the concentration of holes. Now let's take a brief look at n-doping. So to n-dope a semiconductor, we need to choose an atom having an extra valence electron. So let's suppose we want to n-dope silicon. Silicon has 4 valence electrons. So we need to choose an impurity atom having an extra valence electron. In other words, having 5 valence electrons, like for example phosphorus. So phosphorus is an example of an n-doping impurity atom for silicon. So when we insert a phosphorus atom into the semiconductor, into silicon, 4 of these valence electrons will form a bond with the silicon atoms. So the silicon atoms has 4 valence electrons, so we need 4 electrons to form the bond. So 4 of the valence electrons of phosphorus will form a bond with the silicon atoms. So that will leave an extra, the 5th electron, free. And it is this extra electron that will become a free electron and so increase the concentration of free electrons. So we can control the concentration of free electrons, controlling the concentration of impurity atoms. In our example, the concentration of phosphorus. Now in terms of the band structure of the semiconductor, when we insert an impurity atom into the semiconductor, we create what's called an impurity state. And this impurity state, when we are doing n-doping, it's close to the conduction band, like it's represented here. So each atom of phosphorus will create a different impurity state. So you can imagine that we have lots of overlapping dashed lines, each one for a different phosphorus atom. Now, since the impurity state is very close to the conduction band, it's very easy for the 5th electron of the impurity atom, in our example phosphorus, to be thermally excited to the conduction band. When that happens, the electron is now free. It's a free electron, and then it can contribute to current, and it increases the concentration of free electrons. And notice that before the electron was excited to the conduction band, the impurity atom was neutral. The net charge was zero. But now it lost an electron to the conduction band. The electron can move about. So what is happening is that the impurity atom was ionized. So now there is an array of ions with positive charge because the impurity atom lost an electron to the conduction band. That means the electron can move about. But the semiconductor itself is still has zero net charge. The semiconductor is still neutral. Doping does not change the total charge of semiconductors. It only changes the concentration of charge that can contribute to current, free electrons and holes. But the net charge is still zero. We are doping it with a neutral atom. But since each atom was ionized, we have an array of positive local charges in the semiconductors. And notice that these charges, they cannot move. These charges do not contribute to current. They are not holes. They do not increase the concentration of holes. These are fixed ions, and they play an important role in the physics of p-n junction, as we'll see in a future lecture. Now let's take a look at what happens to the Fermi level when we n-dope a semiconductor. So when we n-dope a semiconductor, the concentration of free electrons increase. So that means that the probability of occupation of orbitals in the conduction band increases. So we know that this probability is given by the Fermi-Dirac distribution, which is given by this expression. So these energies will be the energies of the orbitals in the conduction band. So if this term increases, that means that this term decreases, which means that this term decreases, which means that this distance has to decrease. So that means that the Fermi level has to go up. And we reach the same conclusion if we look at the expression for free electrons. Recall that the Fermi level here is just the chemical potential, and the concentration increases with the chemical potential. In other words, the concentration increases with the Fermi level, with the chemical potential. So we can describe the effect of n-doping by either stating that the concentration of free electrons increase or that the Fermi level increase. Both assertions are logically equivalent. So to represent the increase of the Fermi level, I'm going to omit here the impurity state to avoid clutter. And you can notice that now I'm drawing the Fermi level in a higher position than the Fermi level for the intrinsic semiconductor, because now the concentration of free electrons is higher, so the Fermi level has to go up. Now notice something very important. If we take the product of n and p, so this product will involve the product of the exponentials, and here we have the Fermi level with a positive sign, negative, negative, and here the Fermi level with a negative sign. So when we take the product of these exponentials, the Fermi level will cancel, and we end up with this term, which is the band gap. So the product of n and p depends only on the band gap and the temperature and the effective masses through these two parameters. But doping does not change any of these parameters. Doping changes the Fermi level. So when we dope a semiconductor, the product n and p is not changed. But if n-dope increases the concentration of free electrons and the product is not changed, then necessarily the concentration of holes has to decrease. And we can also reach the same conclusion by just inspections of these equations. We already know that increasing the Fermi level will increase n, because n increases with the Fermi level. We have negative, negative, so positive. So the higher this term is, the higher this term is. But p decreases with the Fermi level. We have only a negative sign. The higher the Fermi level is, the lower p is. So n-doping increases n at the expense of p. So it reduces p in such a way that the product is always constant. And in the textbook, there are more discussions about why P decreases and doping, focusing more on a macroscopic description of this process. So now let's take a look at P doping. When we want to P dope a semiconductor, we need to choose an atom having one fewer valence electron. So using silicon again as an example, to p-dope silicon, we need to choose an impurity atom having 3 valence electrons. So boron is an example of a p-doping atom for silicon. So in this case, when we p-dope a semiconductor, the impurity state will be created close to the valence band. That means that it's easy for electrons in the valence band to be thermally excited to the impurity states. So what's happening here is that the p-doping atom needs to borrow an extra electron to form a bond with silicon. For example, boron has 3 valence electrons, but we need 4 to form a bond with silicon. So these electrons are the 4th electron necessary to form the bond. So the doping atoms borrow these electrons from other atoms of silicon, so they receive an extra electron, so they become ionized. So these charges here, they are not free charges, they are not free electrons, they are ions, they are ionized atoms of boron in our example. But since each of these electrons left behind a hole, left behind an unoccupied orbital in the valence band, p-doping increases the concentration of holes. And of course, it also lowers the Fermi level. If this parameter increases, that means that this parameter has to lower. And if this parameter lowered, that means this parameter decreases. So p-doping increases P, reduces N, and the Fermi level is lowered. Now, since we have two different materials, you have N-doping, P-doping, and we also have the intrinsic semiconductor, it's convenient to differentiate between the Fermi level of an N-doped semiconductor and the Fermi level of a P-doped semiconductor. And to do that, we're going to use the symbol N to denote the Fermi level of N-doped semiconductors, the symbol P to denote the Fermi level of p-doped, and I to denote the Fermi level of an intrinsic semiconductor. Now that we have a qualitative understanding of what happens when we dope a semiconductor, we need to find an explicit expression for the Fermi level in terms of the concentration of dopants. Now the Fermi level is no longer in the middle of the band gap. Now it depends on the concentration of dopants, and we're going to find this relation in the next lecture using a simplified treatment. So I see you there.